Now what you find here is uranium-235-92 plus 1 neutron will go to cesium-13855 plus rubidium-9637 plus some neutrons, and I've already showed you in the other video that it's 2 neutrons. Okay, so we can find the masses of each of these different things, so the uranium, the cesium, the rubidium and the neutron, okay? So for example, we're given them in this table here. Now the only thing to be aware of is in this table here, this particle that we're given is actually, these are actually atoms rather than nuclei. So the masses that we're given here are the masses of the atoms, the atomic masses, okay? So for example, the mass of uranium-235 here is 235.043923U. That is not the nuclear mass, that's the atomic mass, okay? Now obviously the mass of the neutron is just 1.008665, so that's fine, okay? And we know that there are 2 neutrons here, sorry. Now, the mass of these 2 neutrons here is just 2 times 1.008665U, okay? The mass of this cesium here is 137.911011U, and the mass of the rubidium, which you can find here, is 95.934284. Okay, now what you should do here really is you should take off 92, the mass of 92 electrons should be subtracted from this number here to give you the nuclear mass of uranium-235, because you've got 92 electrons with it, okay? So this mass here is the atomic mass, so that includes the mass of the 92 electrons. When we're talking about nuclear fission, we're talking about the nuclei. So really we want to get rid of the mass of these 92 electrons so that we get the nuclear mass, okay? Here you should take off the mass of 55 electrons off the cesium mass to give you the nuclear mass. And because this is the atomic mass of rubidium here and that has 37 electrons, you should take the mass of 37 electrons off this to get the nuclear mass. Now, that is all true, but that being said, if you think about it, 55 plus 37 gives you 92. So if we take off the mass of 92 electrons off this, and the mass of 55 and 37 electrons off this side, we're taking the mass of 92 electrons off this side and 92 electrons off this side. So although these are the atomic masses, actually it makes no difference. Okay, you can use the atomic masses here because using the nuclear masses will make no difference because you'll be subtracting 92 electron masses from this side and 92 electron masses from this side, okay? So you can bear that in mind now, okay? But it is just worth being aware that these masses that we're using here are the atomic masses, not the nuclear masses, but for the reasons I've just explained, it doesn't actually make any difference. So the mass beforehand is just going to be 235.043923 plus 1.008665. And the mass afterwards is, the mass of the cesium is 137.911011 plus the mass of the rubidium, which is 95.934284 plus the mass of 2 neutrons, which is that, and that's going to give you, so 235.043923 plus 1.008665, that's 236.052588U, and this is 137.911011 plus 95.934284 plus 2 times 1.008665, which is going to give you 862625U. Okay, so therefore now the change in mass between the two is equal to 236.052588 minus 235.862625, which is equal to 0.189963 U. Okay, and then if you convert that into an energy, it's just 0.189963 times 9.5, which is equal to 176.95 MeV. There we go. Okay. So I'm just going to do the whole thing again, and this time take off the electron masses and use the nuclear masses and show you that it makes no difference. It gives you the same answer here, okay? So what we're going to have on this side is the mass of the reactants here, so to speak, is going to be 235. So we'll call that the mass of the reactants. Whoops. Okay, so the mass of the reactants, and that's going to be 235.043923. And we're going to take away 92 times by the mass of the electron. Now, the electron mass is 0.00055 U. Okay, that's the mass of an electron. So we're going to do 92 times by that. Okay, and then we're going to add on the mass of the neutron. Okay, so that's going to give us an answer of, so we've got 235.043923 minus 92 times 0.00055. Okay, and we're going to add on to that 1.008665. Alright, so that gives us 236.001988 U. Okay. Now, let's do the mass of the products as well. Okay, so the mass of the products here is going to be 137.911011. Okay, and we're going to take away from that 55 times 0.00055. Okay, so that's your mass of your cesium nucleus, and this is your uranium nucleus mass. Right, we're going to add on to that the mass of the rubidium nucleus, so that is 95.934284 minus the electrons, so there's going to be 37 of them. Okay. Alright, and we're going to add on the mass of the two, neutrons. Okay, so if we work that out, it's going to be 137.911011 minus 55 times 0.00055. Right, we're adding on to that 95.934284 minus 37 times 0.00055, and then we're adding on to that 2 times 1.008665. That gives us 235.812025. Okay, now if we work out the mass defect then, okay, so it's just going to be 236.001988 minus 235.812025. So let's work that out. .189963 U. Okay, and what you can see is that that is exactly the same as the mass defect that we worked out before when we use the atomic masses of these rather than the nuclear mass, okay, or the mass of the nucleus of each of them. Alright, so it makes no difference in this situation, okay, but just be aware of that.